A vector function is, or sometimes it's called a vector valued function, is a function from the real line to the vector space R3. Okay, R3 is just another way of seeing this whole space. Okay, um, or we could also map to R2, which is just the plane. Um, of course, we don't have to map the entire real line. We could also just stick to any subset of the real line. But what's important is that you're mapping things in the real line, points in the real line, to points in space through vectors. Okay, you could write the vector valued function or vector function like this, where here's the x component, which depends on t, the y component, which depends on t, and the z component. Could also write it this way. And we could, instead of writing x, we could just write f. So some function f of t takes the place of the x component, and likewise with g and h. These are common ways to see vector functions written. And I emphasize again that the domain is this real line over here. Okay, you don't draw the domain in the actual space as you would in simple functions of one variable. And the range is this whole space over here that you're seeing. And so how do we map these points? So here's t naught, one point in blue. It gets mapped to that blue vector there. That's its value. Okay, when you give r, the vector function, the value of t naught, it gives you back this vector here that's blue. When you give r the value t1, okay, on the number line, so this could be 1, 2, 7, it gives you back this vector in green. And likewise, if you give it the value here, maybe it's 10, it would give you back that purple vector there. So one way to visualize a vector function is to follow the path that the vectors make. So we start out at t naught, for example. We give t naught to the vector function r. We get back this vector r t naught. And let's increase t. As we increase t, we're going to get all sorts of vectors that point in this space. And if we follow the points that they point at, then we're going to get this path. Of course, by looking at the path, you don't know exactly what t value you're at. That's why it's also useful to kind of put these t values in for different vectors to see what the quote time is as you're moving along the path. So let's take a concrete example of a vector function. Here we have the vector function with the x component being cosine t and the y component being sine t. And we're also going to let the subset that we're mapping be on the real line starting at 0 and ending at 2 pi. So right down here is my domain. Okay, start at 0 and end at 2 pi down there. Okay, and I'm going to map some vectors for you. This thing will start at r at t equals 0. If we plug 0 into our vector function, we're going to put a 0 where we see a t. So we get cosine of 0 and sine of 0. That's going to give us the vector 1, 0. And that's the vector that you see right there. This is the vector 1, 0. Now, at a later time, pi over 4, then which vector is r going to return back once we give it pi over 4? Well, we plug pi over 4 into the vector function, which means we're going to plug pi over 4 where we see a t, and we get cosine of pi over 4, sine of pi over 4, and these are square root of 2 over 2 for each component, and this is the purple vector right there. We could also plug pi in. Once we plug pi in, r returns back the vector negative 1, 0, and that's what we're seeing here. If we wanted to follow the trace of this, we would get the path that goes around in a circle in this direction. Okay, it's moving in this direction. So here's an example of another vector function. Here we have the vector function r of t is equal to 4 cosine t, so that's the x component. The y component is sine t, and the z component is t over 2 pi, and this runs from 0 to 2 pi. So now we have the value of the vector function at t equals 0. What happens when we increase t? We move along this trace or path of the vector function. So this is what's going on as t is increasing. You see that we're going in this sort of ellipse due to this 4 cosine t sine t in the x and y components. So here you have a semi-major axis of 4 and a semi-minor axis of 1 along the y-axis. And you could see that as t increases, so does the z component. We could also change the domain. So the domain here is the t-axis, right, which you can't really see. But if we increase the domain from minus 6 pi to 6 pi, you see that it makes 3 different loops around. And if you want to look at only the projection along the xy plane, you will see the ellipse. Okay, so here it is on the xy plane. You see that ellipse. That's what you would see if you looked at the trace of this from the positive z-axis. So you're left with the projection. What happens when you erase this z? The z shows the elevation, on the other hand, how high this thing is getting as t increases.